Now we'll see arithmetic instructions and logic instructions. Let us begin with logic instructions. So it is very simple. We use AND operator and OR operator. These two are the typical logic instructions. So here, when I write AND R1, R2, R3, what is going to happen is it's like ADD. But R2, R3 are ANDed and the result is stored in R1. That's it. Okay. So example, you have some 5-bit register. So generally R1, R2, R3 are 32-bit registers, but I show with some 5-bit registers. Okay. Assume that let's say this R2 is 01010, this is 10010. So only to avoid the much space, then I am using this kind of 5 bits, but generally it is 32-bit operation. So here, when R2 and R3 are ANDed, bitwise ANDed, see 0.1, 0, 1.00, that's quite easy to understand for you people, right? 0.00 and 1.11 and 0.00. So 00010 will be the result. That is about AND operation. Similarly, we can implement OR operation. Whenever we write OR, R1, R2, R3, what is going to happen for this one we will see. So R1 here, R2 here, R3 here. So R2 is, let's say same thing, 01010. Let us take R3 as 10010. Then OR of R1, R2, R3 is nothing but here R2, R3, right? R2 or R3. 0 or 1, 1. Then 1 or 0, 1. Then 0 or 0, 0. Then after that 1 or 1, 1. 0 or 0, 0. In that way we can understand about AND of R1, R2, R3. OR of R1, R2, R3. Now AND of R1, R2 hash value. That means it is immediate addressing mode, correct? In that one. So how things can be implemented we will see. Here I would like to mention one more point, an important point. Actually this instruction is stored in your machine, right? Such a way we have to plan it. That is the idea about RISC, right? So RISC instructions generally designed such a way that they will fit exactly into one memory word. If this is 32-bit in size, because memory words are 32-bit in size, then I assume that let's say we have at least so many instructions we have seen, right? Just recall addition, subtraction, right? Multiplication. Of course I did not mention, but I am going to mention. Similarly AND, OR operators and call, branch, everything. So definitely there will be at least some 64 instructions. Let me assume that I have 64 instructions at least. Then this opcode, this is called opcode, right? Opcode. I'm assuming that let's say we have 3 operands always. Okay. At least in this instruction we have 3 operands. If I give 6 bits for address or opcode, then how many other bits we have? R1, R2 hash value. We have 26 other bits, correct? Now since to address R1 and R2, to mention R1, R2 in the instruction, how many bits are required? 5 bits. Why? Because there are 32-bit registers. To uniquely differentiate them, we need at least 5 bits, correct? So 5 plus 5, 10. To differentiate opcodes, we need at least 6 bits, let's say. Just one of the possibility. Don't remember them that, okay, from now onwards, opcode 6 bits, registers 5 bits. Don't remember like that, okay? It varies, depends on the architecture. Since if there are really 32 registers in any architecture or any machine, the register can be specified using 5 bits. That you can memorize. But don't memorize about this opcode 6 bits. Okay, it can vary. Assume that let's say 6 bits, 5 here and 5 here, 6 plus 5, 11, 11 plus 5, 16. Then you have 16 bits here. Then what about this one, hash value? How many bits remaining? 16, correct? So what I would like to tell you is, here you are going to specify a 16-bit value, correct? So far, in the register R1, register R2, register R3, through this, only you are mentioning 5 bits. It's the address of R1, right? But R1 size is 32 bits, right? So here, generally this is 32-bit, 32-bit, 32-bit. But if you use absolute mode, immediate mode, R1 can be, 32-bit, R2 can be 32-bit. But this is becoming 16-bit. That is what problem. Now, what is my simple question is, if this value is only 16 bits, that means you have at most 16 bit space to mention it, correct? Then R1 and R2 are having 32-bit size registers, right? They are 32-bit registers. Then how AND operation can be done? Sir, what is our problem here? Because when you are doing AND of 32 bits and 16 bits, how you can define it? For that, what we are going to do is, so we can define like this. I show that. This is your 32-bit register, let's say R2. So I am assuming that 0, 1, 0, 1, so on up to 0, 1. All 32-bit values are 0, 1, 0, 1, 0, 1. Now you have some value in the instruction. What is that instruction value? Assume that, let's say, that is 2. Then you are adding 2 with R2, but 2 is now represented with only 16 bits. Then you will be having that 16 bits like this, 0, 1, maybe. What is, how to represent 2 in 16 bits? 0, 0, 0, 0, 0, 0, 1, 1, 0. Then my question, how you do ANDing? 16 bit versus 32 bit. That's why we have to extend it. Since we are talking about logical instructions, then in logic instructions we always extend that with zeros, okay? Because we don't consider about value. It is a logical operation, that's why we simply AND them. When you AND them, what are you going to get? So that means 16 bits will be ANDed, that means appended. So when you do that, what is the result? Now you are going to get 32-bit register, 32-bit result. What is that? So 0.0 anything 0, everything 0, only we have 1 and 0 here, right? 1.0 0, 0.1 0. In that way we can get the 32-bit value which we can store back into R1. Now let's summarize. When you have immediate mode address, when you have immediate mode addressing mode, then we can specify values only up to 16 bits. Then how you AND that with 32 bits is the question, correct? Some students still will have this question. Sir, R2 is having only 5 bits, right? How can you say it is 32 bit? We are mentioning the address of that register with 5 bits. But that register size is 32 bits. Try to understand. So that is the difference between this AND and this AND. So similarly we can understand about R also. So I am not discussing that R, but still we can have that R, R1, R2, #2. This kind of stuff we can do, not a problem like AND. Now we will switch to shifts. So before that I would like to, however, add one more point. You might have this question now. Sir, it is okay for AND because you are adding 16 bits and you are doing the operation, correct? But what was the, what about this one? We used immediate addressing in load instructions, right? Like load R1 and you mentioned address like this, load R1 comma A. This is serious problem. Why? Because load also, let's say, assume that it takes 6 bits. Register R1 takes, let's say, 5 bits. 6 plus 5, 10. Then how many remaining bits we have? After all, 6 plus 5, 11. Then how many remaining bits we have? Only 21 bits. But you said what? In direct addressing mode or absolute addressing mode, A is nothing but memory address. Now, how can I specify memory address with 21 bits? What's the problem? Because memory address here is going to represent what? This is your memory, right? Typically assuming that, let's say you have 2 to the power of 32 memory locations, let's say, okay? That is what my assumption. If there are 2 to the power of 32 addresses, then we need 32 bits to mention the memory address. That means number of bits required to mention the memory address completely is 32 bits. But you have only 21 bits. Try to understand here clearly. This is my general assumption. What is that? My main memory contains 2 to the power of 32 locations. Recall everyone, if you have 4 locations in any memory, how many bits are required to differentiate them? 0, 0, 0, 1, 1, 0, 1, 1, 2 bits, right? Similarly, to identify 2 to the power of 32 locations differently, the number of bits required is 32 bits. Now that's why I am assuming that my memory address is 32 bits. Then how can you specify using only 21 bits is the question. So what's the problem? Why are you having only 21 bits here? Because of RISC architecture, right? In RISC, we are going to keep all that instruction in one memory word, correct? That memory word size is how much? 32 bits. Then you are getting only 21 bits of space. With that only 2 to the power of 21 ways we can mention the address, then only 2 to the power of 21 locations out of 2 power 32 you are going to specify. Is it true? Yes. Then how you are going to solve that problem? Example, I want to mention this address, but your capacity is only at a time mentioning only 2 to the power of 21 addresses out of 1, right? Try to understand. What I am telling is, because of these 21 bits, you will be able to specify one of the address of the 2 to the power of 21 possibilities. But we have 2 to the power of 32 memory location possibilities. Then how can you bridge that gap? For that we will discuss after this point. Okay, so I will be discussing that point after completion of this logical shifts and arithmetic shifts and rotations. After that we will see. So just ask yourself and keep that question open, right? Now we will see shifts. After that I will explain. So in the shifts, first we start with logical shifts, after that arithmetic shifts. So whatever the shifts, we are going to have another flip-flop, that is called carry flag. Okay, so there will be one more bit called carry flag. So there will be some other flags, generally like overflow bit, everything, you know that, right? So what is the help? If you have an overflow bit, overflow flag, what are you going to do with that? So that overflow flag supposed to, just use your common sense. Generally you have a overflow flag means that should become 1 whenever there is a arithmetic overflow, correct? So similarly there is a carry flag. So this is going to help you in some of the operations, like some of the multiplications and divisions. Okay, now remember that. So whenever you do logical shift or arithmetic shift or rotation, we will be using a flag called carry flag. Okay, assume that initially it is 0. Now with that I am going to explain you what is the meaning of logical shift, what is the instruction for that. Assume that, let's say this is a typical instruction, left shift. And remember one thing, we can do logical shifts in 2 ways, logical left, logical right, correct? So similarly we will be having arithmetic shifts, arithmetic left, arithmetic right. First of all, let us begin with logical shifts. There are 2 shifts, one is logical left, logical right. See, let us do first logical left shift. L means logical, shift left, L means left. Okay, so L shift L, R1, this has to, this is going to tell you how many times you want to shift. Okay, this is number of times you are going to shift. This hash to means what? We are going to shift register R1 2 times. Okay, this is the typical instruction generally possible in machines. Okay, so what is going to happen, we'll see. Very easy, because it is logical shift, then we don't worry about sign or anything, simply we shift 2 bits. When I shift 2 bits, first of all, when I do first shift, this 0 comes here. Okay, so everything will go through carry flag from now onwards, remember it. So because we can use this carry flag in some operations, I will explain. Example, let's say you are doing a big multiplication. At that time, so we are going to use this shift operation. Then when that shift operation is giving carry or not important for that algorithms, that's why, so we use carry flag. That is enough to remember. Okay, so we are not going to further details at this moment. Now what happens? The remaining bits will be as it is, like 1 0, so on 1 1 0. Sir, there is one position which is emptied here when you shifted left side. What are you going to fill? Since it is logical shift, we are going to fill 0. That's it, always 0. Now logical shift right side and register R1. And remember one thing, because of this operation you spoil your register, correct? Yes, that is the way you wrote, right? If you don't want to spoil, you can specify another register here, not a big deal. Now left logical shift right, R1 3, that means R1 is shifted 3 units and the result is stored in R1. That is what the meaning. Okay, now again you will have carry flag. So all the result will go through this carry flag first time. And I think forgotten to do shift 2 times, correct? Only 1 time I did, but we said here 2 times, right? Let us do logical shift left side 2 times. This is first time result. Second time this 1 comes here, right? Then the result will be like this, 0, remaining things whatever it is, 1 1 0 0. There is one more bit which is emptied now, that means one more position at right side, that will be filled with 0. Okay, now for 32 bit this is the idea. Example, you have 4 bits, then what is the output we will see. If you have only 4 bits and carry bit initially 0, whenever I do left shift of this one by 2 units, so what is going to happen is, first time 1 will come here, then this 1 will be cancelled and here 0 comes. Okay, now one more time if you do, this 1 comes here like this. So simply extend this to one more step and write 0 here. What happens? It will be 1 0 0 0 0. Now you shift it. When you shift it, this 1 comes here, right? Then it will be again 4 zeros. So this is the way shift will be applied. Similarly here also, Let us do here left shift, logical shift of right R1, R1 has 3. So 3 times. Then this 0 comes here, next time 1 comes here, next time 0 comes here. Okay. Finally 0 comes here, this 1 0 will go out. So they are gone. Now when these 3 are shifted like this, entire thing by 3, then 1 comes here. Then whatever the remaining thing is there, that will be there. Okay. Now slowly, so all these bits will be there, 1 0 1 0 1 0. But when you do right shift 3 times, then 3 empty positions will be formed. There we have to write 3 zeros. That is what final answer. Okay. So this is about logical shift of right side. That's it. Now similarly we can talk about arithmetic shifts. What is the difference between logic shift and arithmetic shift is, in arithmetic shift we will be following sign extension. That means it is arithmetic shift, right? Then we will be worrying about sign bit. Okay. So don't worry, I'll explain with one example. Here also arithmetic shift will go through carry flag. Okay. Let us do arithmetic shift L R1 R1 3. Okay. That means we are shifting R1 by 3 units. Since it is arithmetic shift and especially it is left side, we have to shift left side. So that's why I am keeping here carry flag. Initially it is, let's say 0. Okay. So now here you have 1 0 0 1. I am going to write the result now directly. What will be the result we will see. First shift R1 by 3 units. When I shift R1 by 3 units, first time 1 will go out, second time 0 will go out, third time this 0 will go out and that will come here. Okay. First of all we will see one iteration. Only one shift by 1 unit we will see. What is the intermediate result? So 1 comes here. Then remaining things are 0 0 1 0 1 1 as it is. Then remaining bits whatever. Then 0 comes here, 1 comes here, 0 comes here. There is a space. Sir, what to do in this space? Simple. So when if it is left shift, then simply add 0. Okay. It is like logical shift only. Okay. So that is about one shift. But we have to do it two more times, right? When you do 2 more times, next time when you do, this 0 comes here, right? That's not a big deal. So this 0 comes here, this 1 comes here, 0, 1, 1. Again you get one empty space. Again that will be filled with 0. When you do one more time, then this 0 will be jumping here. Then this 0 will jump out. Then this 0 will come here, this 1 comes here, 0 comes here. In that way order is same, but the last bit again will be 0. In that way result is 1 0 1 1, remaining whatever the bits followed by 0 1 0 0 0 0. It was 0 1 0. This 0 1 0 moved to towards this left side by 3 units, and the remaining bits will be filled with zeros. So that is about arithmetic shift, right? Now we'll see arithmetic shift right. Whenever we shift right, how to do that? So this time let us take carry flag this side because we are shifting right side, right? When I shift right side by 2 units, what is going to happen? We'll see. This is your resultant R1. So 2 times. First 0 comes here. Assume that 0 is carry flag is 0. Then when I shift by 1 unit, this 0 comes here. So no change. Now the remaining things are like this. So this 0 is gone. Right shift 0 dot 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 as it is 1. I am showing only shifting by 1 unit. 1 1 0 1 0 0 1. Because when you shifted right side, there is an empty space. What are you going to do is a question. So what we are going to do is, when you do right shift, then see it is arithmetic. That means we have to worry about sign bits. It is a negative number. When negative number is shifted, suddenly it should not become positive number. Okay, it has a purpose. So that's why I will tell you the reason why we do sign extension, because we have to preserve the sign bit of that one. That's why what we do is we add one more one, so that example when you have 4 bits, then we can understand. Example, you have 1 0 0 0. You are shifting right side. When you shift right side, this is -8, correct? Now when you shift by 1 unit, you are going to get 1 1 0 0. Then that will become what? -4. So the beautiful property of this arithmetic shifts is, when you shift right side, the value will be halved, and when you shift left side, then that value of that register will be doubled. Okay, if you see as a value, because arithmetic means what? We have to focus on values. Example, you have a positive number 0 1 0 0. Let us do left shift. When you do left shift, what is going to happen? We'll see. So 0 goes out, then 1 comes here, then 0, 0. Here what we write? 0. Then what is going to happen? 8. What was it before? 4. 4 to the 8. So left shift will make your number double and the right shift will half your number. So to have that property, what we have to do is, whenever sign bit is moved, that means whenever you do right shift, sign bit will be moved, then we have to replace that empty position. You are going to get empty position, right, when you do right shift. Then sign bit will be emptied, that will be up, that will be filled with same bit as the previous bit. Okay, otherwise sign bit will be extended. Understand? Okay, now that's why here finally what is going to be the result, we'll see. Let us consolidate it. See, it is negative number. When you do right shift, one position will be emptied. Here you get one position. Now this 1 comes here, this 0 comes here, this 0 comes here. Sorry, we have to do 2 shifts, right? Let us do 2 shifts. When you do 2 shifts, what is going to happen is, so 0 first comes here, after that 1 comes here. Then carry flag will become 1. Now, so this 2 positions will be emptied, you know that, right? So when you do right shift, there are 2 empty positions. After that, this 1 comes here, this 0 comes here, this 0 comes here, this 1 comes here, then 0, then 1, then some gap, correct? Followed by, it was 0, 1, I think, 1, 0, right? See, when you do right shift, this 0 will be the last position. Then, when you shift first time, 1 comes, so finally this 1 will go here, correct? You understand that. So here I show, initially it was 0. So carry flag is 1, right? Now you can see, where is your 0? Because of 2 shifts, 0 is gone. So this 1 reached to carry flag. Now this 0, which was in the third position, become first position from left side. Then remaining things are as it is, like 0 after 0, some numbers, followed by 1. Yes, 1, 0, 1, 0, 0, 1. Then there are 2 empty positions. What to do? Because we have to follow that property, then we have to do the sign extension. That means we have to add ones. Blindly remember it. The difference between logical shift and arithmetic shift is, in arithmetic shift, when you do right shifts, then the emptied positions are filled with sign bit. That's it. Apart from that, everything is same as logical shifts. In logical shifts and arithmetic shifts, and finally the data goes through carry flag, correct? So that carry flag will be remembered too for some other reasons, like to use them in big multiplications and everything. Remember it. Okay, now we'll see rotate operations. So rotate operations are 4 types: rotate left through carry, rotate right through carry. So what is the idea about rotations is, so when you rotate it, your data will not be lost. We will be storing back and we will be holding them in the register itself. When you are shifting from left side, when you are rotating from left side, the data comes back to right side. When you are moving from right side, that means when you are rotating from right side, the data comes back to left side. That's it. Now, here also we will be having carry flag. Whether you use it or not, but carry flag will be updated. Okay. So we have 2 operations: rotate left through carry. In rotate left also carry will be updated, but the rotation will not go through that carry. We will try to understand that with example. So for simplicity, I am using only 5-bit registers. We can extend it to 32-bit also. Example, let's say you are rotating the register R1 left side by 2 units, okay, and you are updating that register R1. What is going to happen, we will see. First, when you do rotation by 1 unit, systematically we will see. Rotation by 2 units equal to rotation by 1 unit followed by 1 unit. Let us do first unit. When you do that, so this 0 goes, rotate left, right, this 0 goes here. Remember it, okay. Then still carry bit is 0. At the same time, because you are rotating, that 0 go to this side. So 0 comes here. These 2 are essential steps. When you shift left side, then that 0 comes here. Now this 0 is nothing but here. At the same time, it will come back. Now remaining story is as it is. When this 0 comes to this place, this 1 will move here. Then this 1 will move here. This 0 will move, then 1, then yes, 5 bits are done. This is rotate left, but not through carry. Okay, we are not using carry in the rotation. Next, again do one more rotation because we need 2 rotations, right? When you do second time, first this 1 will come out and it will be stored here. So carry flag will become 1. At the same time, that 1 comes here. Okay, so 1 comes here. Let us write 1 here. Then, so better what you do is, so you do the result in the next step. So let me take temporary space here. So here this is the result of first step, this is the result of second shift. So after first shift what happened? 0 came here and you got 1 0 1 1 0, correct? Now second time this 1 comes here. Now at the same time 1 goes here, then this 0 comes here. Now simply move that 1 to here, then do without C, try to do the rotation. When I do rotation, what happens? This 1 comes here, right? Then this 0 moves, then this 1 comes here, then 1 here, then 0. See, 0 1 1 0 followed by 1. But apart, we have also carry. Now we will see rotate left through carry. We try to understand that. So here this carry is also involved in the operation. That is what I would like to tell you. Okay, let us do that. When you do rotate left through carry, what is going to happen is 2 units, right? First we do 1 unit. When you do 1 unit, Mr. C 0 or C or you are also involved. Then when we do left shift, then 0 comes here first, right? Then this 1 will go ahead, 0 1. This 0 comes here. In that way, so it will be a circular shift, right? Now one more step. When you do one more step, what is going to happen is same story. First, this 1 will come here. Now this 0 will come here. Then this 0 will come here. This 1 will come here. This 1 will come here. This 0 will come here, right? Then the result is 1 0 1 1 0 0 here. But here, if you do rotate left shift, the result is 1 0 1 1 0 1. There is a difference or not? Yes. So that's why rotate left and rotate left through carry are different. Okay. So this is about rotations. Sir, what about rotate right and rotate right through carry? You can do that, right? It's not a big deal. If you understand left side, you can understand right side. So this is all about the remaining other instructions. Okay.